Mr. Chairman. For our foreign guests, I'll give my talk in English. The title of my talk today is Multi-Objective Optimization of Steel Fusion Welding, and is in collaboration between the University of Salento and Enginesoft company. The reason of this research is that there are very few information or focused information on the relationships between microstructure, fracture and fatigue properties of steel fusion welding. And in some cases in particular you can find very good data on just single experiments, just one steel in which few processing parameters are related to the mechanical properties or to the microstructural evolution, but a very broad conclusion cannot be done because there are not so big data available. In particular, the microstructure of fusion welds are strongly influenced by the properties of heat-affected zone, which is directly related to the history of heating cooling during the processing of fusion welds. And so, in this way, we choose to make a lot of experiments in terms of mechanical properties, tensile, fatigue, and impact strengths of different fusion welds, relating these properties to the history of the weld in terms of current, voltage, heat input, and so on, number of passes, as I will show you later. In this way, we are able to compute such data through a multi-objective optimization tool. In this way, we have an instrument that trains on the job and give us additional information which are the ways to be followed to optimize some properties in terms of microstructural evolution, increasing tensile strength, increasing fatigue and impact strength. In this way, it is possible to have so many data available to have precise design of experiment and optimize the situation of each kind of steel or globally, depending on the final goal of the study. The instrument we employed in these studies, Mode Frontier, is a commercial tool which permits us to study a lot of processing conditions and giving us as output many mechanical and microstructural data, and in this way give us the possibility of analyze a large number of experimental data going to the optimization of the mechanical properties. The number of experimental data we analyze is 600 experimental conditions in terms of different thicknesses, different input, different voltage and current during the welds, and actually in terms of 600 data in terms of tensile properties, fatigue and impact strength. 580 were employed to train the system, and the remaining 20 were employed as validation for the final properties of the material. In this way, it is possible to train the response surface we obtain through the analysis of the input and output experimental data and correlate to the remaining 20 properties to a delta error, which give us the goodness or not of the analysis we perform. This is the workflow which is worked by Mode Frontier. The welding processes is divided into a lot of input parameters in terms of weld geometry, the thickness of the weld, the angle, the number of passes, which strongly influences the final properties of the welds, the welding speed, the welding current, the voltage, and heat input. Here you can find an example of the different steels we analyzed in this study, in which we fixed the composition. You know that commercial available steels have very broad ranges of composition. We fixed the composition in terms of the same kind of steel for each data we give as output. There are a lot of different kind of steels, carbon steels, stainless steels, duplex, high strength low alloys, and so on. And here you can find the table of the different input parameters we employed in terms of thickness, from a few millimeters, a couple of millimeters to 8 millimeters in thickness, the angle, the total number of passes, and for each pass or each group of welding passes, the different input parameters in terms of current, speed, voltage, and heat input. And this work has been done for all the welds. These are the output. We measure the residual stresses through X-rays, hardness profile, phase formation, always through X-rays measurements, and sometimes where the data was not so clear with microstructural observation to optical microscopy, tensile strength, fatigue strength, and impact strength, all at room temperature. In this way, in different zones of the weld, depending on the thickness, we measure the residual stress and micro-hardness profile. For example, for bigger weld, we measure in 3 sections the residual stress and the micro-hardness profile, while for thicker welds we measure just in the middle of the weld. And here we checked the microstructure in terms of martensite starting and finish formation, bainite, perlite, ferrite, and austenite, taking into account the same point in which micro-hardness and residual stress was measured. In this way, we are able to check point by point the situation of the evolution of microstructure and mechanical properties of our welds. And here we measured the tensile properties, fatigue, and impact strength with respect to the base metal resistance in this case. Here you can find an example of the bigger welds we studied. These are almost 80 millimeters in thickness, 316 carbon 1020 and 1045 steel. Now the first results to be analyzed were the global ones. So we tried to give behavior of the output in terms of all the data belonging to our investigations. And in order to give a general law and a general way to be followed to optimize the welds and the consequent mechanical properties. In particular, we found that hardness increasing the angle of the weld up to 70 degrees and then decreases as increasing the alpha angle. Hardness increases as increasing impact strength, residual stresses, and ultimate tensile strength up to intermediate values and then decreases. For the impact strength, it increases at increasing the angle and the voltage, and then decreases as increasing the welding passes. The number of welding passes is strongly important in the weld's behavior because the thermal history of the material and the transformation history is strongly related to the number of passes and which is the heat input at each pass. The impact strength we found is optimal for intermediate values of yield strength and ultimate tensile strength. This means that if you need very high tensile properties, you have not so optimal values in terms of impact strength. And here you can find the so-called correlation matrix. This is the global correlation matrix in which they are described, the correlations between all the input or output parameters in terms of weight. In this way you can find that for each single point you want to analyze, you have the weight on, for example, residual strength, yield strength, impact strength, and so on. In this way you are able for a lot of investigations, which can be, for example, the weight of heat input on fatigue limit, or the weight of heat input on residual stress profiles, and so on. And you can do this job for all the experimental data you have available, or for each single steel that you want to analyze, and so on. So it is a very fast and very useful instrument to understand what is going on during your experimental evaluations. And here you can find some examples for some single steels, because we focused, after the global evaluation, we focused on each single steel that optimizes each single situation. Focusing on mechanical properties for IEC 304 and Weldux 1100, the highest values are in correspondence of low and intermediate heat input. For lower heat input, you have a strong decrease in mechanical properties. For IEC 321, the optimal is for intermediate heat input. If you have a very big or very low heat input, you decrease strongly in mechanical properties. And for IEC 316, 409M, 4340 and high strength low alloys, they correspond to low heat input. So you find a very broad different situations. For each kind of steel, you have a very broad processing conditions to be employed, and very different processing conditions to be employed for optimizing the mechanical properties. For example, for IEC 1020 and 1045, both fatigue limit and impact strength increase with increasing residual stresses. So if you are able, compatibly with the geometry of the structure and so on, to have an increase in residual stress for this kind of steel, you strongly increase the impact strength and the fatigue limit. For IEC 304 and Weldux 1100, both fatigue and impact strength are high in very broad range of residual stresses, so they appear very not influenced by the residual stresses. IEC 316, the strength is maximum for intermediate residual stresses. For 409 and high strength low alloy, the impact and the fatigue strength correspond to very high residual stresses. And for IEC 321, the impact strength and fatigue life are in correspondence of intermediate residual stresses, while for 4340, both fatigue and impact strength are high for high to intermediate residual stresses. And finally, we tried to correlate the mechanical properties, going back to the input parameters, optimizing the input parameters, having as a consequence the optimization of mechanical properties by taking into account the microstructural evolution, because the microstructural evolution of such steel welds are strongly influenced by the situation in the microstructure. So, for example, for IEC 1020 and 1045 and 409M steel, the welds show the best fatigue limit and impact strength for ferrite martensite rich microstructure. So if you are able to your processing parameters to induce just a ferrite microstructure, ferrite martensite microstructure, you have the optimal situation in terms of mechanical properties. For such stainless steel, it is difficult to relate to microstructure evolution, because it is always the same. And for IEC 4340, the best fatigue life corresponds to martensite ferrite microstructure, while the good fatigue life and high impact strength correspond to martensite ferrite austenite microstructure. So you have to choose if you want just the best fatigue life, not taking into account the impact strength, but if you have good behavior in terms of both fatigue and impact strength, you have to induce a very different microstructure through your processing parameters. And we found finally, because you have to indicate a macro parameter in this evolution, you have to say, okay, I want just this weld through this heat input, and so you fix all the processing parameters during the weld. we found that for easy 1045 and 4340, the fatigue properties and high impact hardness are experienced for low heat input. For 304 and duplex 2205 still follow the same behavior. The high strength low alloy and military A11 and so on. The best correlation is between impact and fatigue strengths are in correspondence of intermediate heat input, and in this way it was possible finally to identify the best processing conditions for the optimization of both mechanical and microstructural consequent evolution in our steel. This is some examples of the validation phase. We fixed some conditions for the 20 steel, but we chose just 7 different conditions, and you can see that the database was very good as a provisional instrument for different conditions not experienced by the experimental work. These are in terms of micro hardness profile and residual stresses profile, and these are in terms of mechanical properties, yield strength, ultimate tensile strength, fatigue life, and impact toughness. For the microstructural evolution, the system doesn't work so good in terms of previsional of the evolution. This means that just for this kind of work, the system needs much more experimental data to be trained in order to be more precise on the final evolution of the microstructure, because it's very complex, martensite, austenite, perlite, and mixing of 2 or more microstructures, and so it becomes very difficult. In conclusions, this way of work allowed us to build a very big database on many different kinds of fusion weld, gas metal arc fusion weld for steels, and is an instrument which is open, so it can be improved in its performances on the job. So you introduce new data, and so it works much more good, and so it's an open database, and it allowed us to have a good provisional tool for the mechanical properties, and we are working on to have an optimization in terms of the prevision of the evolution